SwayamPrabha. Digital India. Educated India.
Hello and welcome back to the discussion sessions of the course on production technology, science and practice, theory and practice. Now, let me remind you that in the last session we have discussed, or we started discussing rather, the mechanics of metal cutting. Now, I told you that the mechanics of metal cutting, the first treatment given to the metal cutting, all right, and it was given way back in 1944 by Merchant and Ernst. These are the scientists, and since then that Merchant's theory and the Merchant's first equation, Merchant's circle diagram, they are popularly used in metal cutting to understand the mechanics of machining, to understand the inside, to see the inside of the metal cutting. Now, in here I will remind you that what we did is, what we said is that if the workpiece, when it is, the excess workpiece is in terms of chip which is removed, and when the chip is moving over the rake face of the tool at a constant velocity, let us say VCH, then the workpiece material has to be rigid and perfectly plastic, homogeneous, so that the VCH could move at a constant velocity when only the resultant forces acting on the chip from the tool side through the rake face and from the workpiece side through the flank through the shear plane are equal, opposite and collinear. So, then we have resolved the R and the R prime into components. R is two components F and N. F is parallel to the rake face of the tool, N is perpendicular to that. So, N, because of the N, the F is created, right. N is the normal force and F is the friction force. Similarly, the R prime, which is the resultant force acting on the chip from the workpiece through the shear plane, we have resolved into two more components Fs and Fn. Fs is parallel to the shear plane and Fn is the normal to the shear plane. Then we said that if alpha or phi change, in that case all these components, four components, that is F, N, Fs, Fn, they will change the direction. So, we do not have any unidirectional or unique direction of a unidirectional, okay. Or rather we should say that we do not have the directions as unique, they always change with the change in the phi and the alpha. So, therefore, we resolved the R prime into two more components which actually will not change with the change in the phi and the alpha, and these components we said as the one component which is parallel to the VC direction. So, therefore, that component, since it will have the responsibility of power consumption, this component is called the cutting force, because it is parallel to the cutting velocity, and perpendicular to that is the thrust force, which is also the resolved force of the R prime. So, altogether we have 6 components, and those 6 components can be related with these 8 assumptions that I have already told you, all right, and all those assumptions say that this treatment given or this model, okay, Merchant's model is actually 2D, okay, 2 dimensional, and this is for the orthogonal cutting, not for the oblique cutting, okay, because all these assumptions, if you see, all these assumptions are valid for only orthogonal cutting, and in oblique cutting these assumptions are not valid. They are correlated with the 3 angles: shear plane angle, rake angle and the friction angle, and we said that all these could be converted through the FC and FT, because we measure the forces through the FC and FT only. Okay. So, then we said that the Fc can be found out through the Fs, all right. Now, Fs is the shear force, okay, or the which is parallel to the shear plane. So, therefore, shear force Fs along the shear plane, this can be written as the area into the shear plane area into the stress, okay, and this is the shear stress. So, the area is given by the width of cut, uncut thickness divided by sin phi. So, if you go back to this, well, I mean if you go back, like I will draw it here, okay, again I will exaggerate that, all right. Let us say this is the workpiece, this is the tool. So, this perpendicular to that is T1, okay. This angle is phi. Width of cut is, if you see the, I mean this is the width of the workpiece, okay. So, let us say this is the width of cut W. So, W into T1 by sin phi, which is this length T1 by sin phi, this will be the length, oh, sorry, the area, and this is the stress. So, stress into area is actually the Fs. So, we are expressing the Fs through the area of the shear plane. So, let me write down here that this is the area of the shear plane, okay, of the shear plane, and this is the shear stress. This is the shear stress which is applied on the during the process, let us say, where W is the width of the workpiece under cutting, this is the width, and T1 is the uncut thickness. This T1 is the uncut thickness, tau s is the shear strength of the work material. So, this is equivalent to the shear stress, all right. This I said to you earlier also in our discussion. Now, therefore, the Fc which was in this way, we are putting the value of Fs in this and we get this equation, okay. Put the value of the Fs which is W T1 by sin phi, and this is the rest of it. So, the power power P, as I said, is equal to the product of Fc and the Vc. Fc is the cutting force component, Vc is the cutting velocity, which is pi d and the n. As per nature of taking path of least resistance during the cutting, phi takes a value such that least amount of energy is consumed, or P is minimum. Let me explain it to you that always in nature everything goes to the least resistance, all right. If you remember, we said that in case of the lattice structure, for example, all right, the movement of the defects, dislocations, all these say that everywhere the movement is to the least resistance, where the resistance is less. So, in the case of metal cutting also, during the metal cutting, as per the nature, what it happens is that the cutting process itself adjusts the phi in such a way that the minimum power is consumed for the process, for the machining process. This is nature, okay. This is what happens in metal cutting as well, all right. So, that means the P will be minimum. Now, the P, if you see here that Fc you put the value and with the Vc. So, if you multiply with the Vc, here all these terms will be actually constant if you take the P as a factor of phi, function of phi, meaning that as the phi is changing or alpha is changing, let us say here the phi is changing, we have taken as a function of the phi. So, here this will be constant, that is the numerator, and the denominator will not, because here we have the phi, okay. So, if we take the power as a function of the phi, then this equation can be said as the numerator divided by denominator, numerator being constant and the denominator is this sin phi cos of phi plus beta minus alpha. Okay. Now, for the least energy, for P to be minimum, the first derivative of this equation has to be equal to 0. Okay. And if you take the first derivative of this, because this is constant, all right, because what happens is that this to be minimum, this has to be maximum. Okay. You understand that if P of the power, which is a function of shear plane angle, has to be minimum, the denominator has to be maximum. So, therefore, the first derivative of this should be equal to 0, and if you take that, it will actually give you the 2 phi plus beta, this is the friction angle, minus rake angle is equal to pi by 2, and this equation is known as the Merchant's first equation. All right. Now, from that shear stress, we know that this is the shear force divided by area of the shear plane. Okay. And area of the shear plane, we have already seen that this is the area of the shear plane, WT1 by sin phi. So, therefore, the shear stress, this is equal to Fs, we already found out, Fs is here, Fc cos phi minus Ft sin phi, okay, into sine of this theta, because sine of phi, sorry, Fs, because it will be divided by Fs divided by W and the T1. This is how the shear stress is coming. Now, if you see here, why I am showing that here is that if you measure Ft and Fc and Ft, and if you have the value of the phi, you can actually find out the value of the shear stress which is required, because the W and the T1, these are the physical parameters. This is the width of the workpiece, okay. T1 is the uncut thickness, these are physical parameters. Similar to the shear stress, we can find out the normal stress, which is, if it was Fs by As in case of shear stress, this will be Fn, because it is a normal stress, divided by the same area of the shear plane, because we are measuring along the shear plane. We are measuring, or we are determining analytically what will be the shear stress and the normal stress along the shear plane angle. Okay. So, therefore, here it will be the area of the shear plane. Now, therefore, this will be equal to, put the value of the Fn from the Merchant's, which is through the Fc and Ft, okay, and this results to this equation, that this is the normal stress, which is this value. So, again, by measuring Fc Ft, you can actually find out the value, analytical value, by knowing the physical parameters and the shear plane angle. Shear strain in the chip formation, okay, can be found out in the following way. Well, shear strain, I have already shown it to you, that what is shear strain. I will once again show it, that if this workpiece has been strained to this way, all right, let us say, and this much is x we said, this much we said as the b, then the shear strain was equal to x by b. This I already told you earlier. Now, in case of metal cutting, the shear strain therefore could be found out using this concept, that the chip which is flowing along the rake face of the tool can be assumed to be segregated, okay, as if we are taking this into different slices. All right. So, the entire chip, we are assuming that each one has a particular thickness. So, this is the kind of a card pack, playing card pack, you know that. Okay. So, playing card, each playing card is having some width, all right, a thickness. So, that thickness is the same for all the playing cards, and we are assuming that they are in the slices. So, the same thing we are assuming here, that the chip is sliced, and each slice has a same thickness. All right. Now, when the force is applied, okay, let us say you have a stack of playing cards and you hold it like this and push from the top gently, then what happens is that whole thing will be sliding in the following way as it is shown in here. Let us assume that it is equivalent to that stack of the playing card. Okay. So, if we draw this, all right, and if we take this triangle, let us say we will consider this triangle, okay, here, all right, then see what happens. Let us say this is A, this point is A, this point is B, and this point is C. Okay. Now, from point B we can take a perpendicular, and this we have called as the D. Okay. So, this is shown in here, that this is the B, okay, this is A, and this is the C. So, if you see this slice, this first slice for example, the A, this chip, this slice has been deformed up to this AC, isn't it? AC, because if the tool had not been there, this chip would have been could slide up to this. Okay. So, I will come to this diagram. First let me explain it from here, that AC is the deformation which is equivalent to x in this diagram. Let me tell you, that would be easier for you to understand. Okay. AC is the amount of deformation that has taken place as the shear force is applied to the workpiece. Okay. So, this is equivalent to x. Then D is the perpendicular from the point B on the AC. So, therefore, this is the shortest distance, and the distance between these two layers, okay, will be the this value, this is the BD. So, BD will be equivalent to B here, small b here. So, therefore, the strain from this shear strain from this diagram could be said as equal to AC divided by BD, because AC here in this case x and BD is the B. So, shear strain is x by B, which is AC by BD, and then you can find out that AC is equal to CD plus AD. So, then it is divided AD by BD and DC by BD, it will get you that the shear strain is equal to AD by BD from this triangle. Okay, you can find from AD by BD from this first triangle, this is equal to tan of phi minus alpha, all right, and the DC by BD, this will be cot phi. So, overall you will find out that the shear strain is equal to tan phi minus alpha plus cot phi. So, this concept is the same as shown it here, that if this is the layer with the thickness of delta, okay, and this layer could have gone to this port this much had the tool not been there. So, we are considering this triangle, this is the triangle, and from here we are putting a perpendicular to the AK, let us say. So, here also you will see that the AK is equivalent to this AC or equivalent to x. So, in this case it will be AK divided by ON, okay. AK is AN plus KN divided by ON. So, it will be AN by ON divided by KN by ON. So, it will be ultimately the same thing exactly. So, this is just to understand that how we can make the equivalent of this diagram in case of metal cutting. Okay. Now, the strain rate, during the discussion of material, I told you that the strain rate involves time. Okay. So, therefore, the strain rate is this delta S by delta Y, okay. Delta S by delta Y is here, I will come to that, divided by delta T. That means, delta S by delta Y, we are taking this one, delta S by delta Y, okay. This we have taken as the delta Y. If we see from this diagram, this is the diagram, this is the shear plane angle, this is the cutting velocity, this is the shear velocity, and this is the chip velocity. So, otherwise it will be difficult to find out the value of the delta S by delta y and the 1 by delta t. So, we take the help of the diagram, this diagram, and we say that in this diagram the VCH, VC and the VS, they can be coupled in this way, because you see the VC is in this direction, VS is in this direction and VCH is in this direction, and these are the angles. So, these angles we have already seen that this angle will be alpha, that is the rake angle, this angle will be the shear plane angle between the VS and the VC, and so on. So, if you take that, then you use the sine rule and you will find that the Vs divided by sine of the opposite angle 90 minus alpha is equal to Vc, Vc is here, divided by sine of opposite angle 90 minus phi minus alpha is equal to Vch divided by sine of phi. Okay. Here it is written, same thing. Therefore, the shear velocity we are finding out first. Shear velocity is equal to cos alpha, this is from here. Shear velocity we are finding out through the Vc as Vc, and the cos alpha, this is equal to cos alpha, isn't it, divided by cos of phi minus alpha, because it is 90 minus phi minus alpha. So, this is divided by cos of this, all right. So, as you understand that why we have done that, delta S by delta t into 1 by y we can find out, isn't it. This we can say that this is delta S by delta t and the 1 by delta y. Okay. So, delta S by delta t we can find out as in terms of Vs, because this is the shear velocity. So, for each of these layer thickness, for any given layer thickness, what will be the delta S by delta t will define the strain rate. Okay. So, this is of course not right there, here we have the 1 by delta t, and this can be equivalent to delta S by delta t into 1 by delta y, and this is given as this, that is right. All right. Now, well, here what we are seeing is again if we know the phi, okay, alpha will be known because we are using a tool which we have decided which tool we will be using, and for that tool the rake angle we have given, okay, according to our choice. And I have already discussed with you that depending on the workpiece material hardness of the tool material, we have to find out the value of the alpha. Okay. So, then if we can find out the phi, this is the shear plane angle, we can analytically find out the value of the shear strain, okay, as you can see. We can find out the value of the strain rate, we can find out the value of all these things, shear stress, normal stress, also the theoretical values of the or analytical values of the Fs, Fn and so on. How to find out the shear plane angle? There are two ways. One way is shown here, this is found out, this is experimental, that means there is a device which is called the quick stop mechanism, and on the quick stop mechanism there is a cylinder which can actually move freely, and this is the movement is stopped from here by a shear pin, all right, and on this cylinder loosely fitted here on this slide, okay, there is a workpiece, and at the back of that there is a tool with the tool post, and it moves forward. When it moves forward, the tool is actually at the another level which will just touch the workpiece, which will remove the workpiece material from here. Okay. But this is the tongue, this is behind the tool. When the tool is removing the material, after some time this back tongue which is at the back of the tool, it will actually start contacting with the cylinder. The cylinder is loosely fitted on this, only stopping is, you know, it can be stopped from moving to this direction by the shear pin. So, when the tool has started removing material, then this tongue will come from behind and it will hit this cylinder, and the cylinder will go come forward, breaking the shear pin. Okay. As a result, what will happen, that the machining process will be stopped because it is already broken and it has come forward, and we will get the workpiece with partially made chip. This is important, okay, for the measurement of the shear plane angle. It is important that we get a clear picture of the chip, all right, and it is something like this. The workpiece can be graduated like this, all right. These are the this can be painted on the workpiece, and as this is given, tool is penetrating the workpiece. So, this graduation, these lines will be deformed. These are painted, these are made on the workpiece. So, then if you see that whenever it started deforming, these are not deformed, okay, because the stress is not, or the plastic deformation not taking place here, plastic deformation not taking place here, okay. But at this point, that is along the shear plane, it will be deformed, and you will clearly see that which points, along which points the graduation, these lines started deforming. So, if you join them with the tool point, with the tip of the tool, you will get a straight line, and that straight line makes an angle with the cutting velocity vector, which is equal to the shear plane angle. So, of course, for this measurement there are two difficulties and there are two inaccuracies, therefore, may creep in. One inaccuracy is that you have to exactly stop the working machining process, so that a clear picture can be found out when the chip is being formed. Okay. The second error or the inaccuracy may chip in when actually this is to be connected. Okay. These points to be connected with the tool tip, because otherwise you will not, you understand that you will not get the accurate value of this angle. Okay. Because of that fact, the measurement is not followed popularly in practice, and the value of the shear plane angle is taken analytically. So, let us see how this shear plane angle can be analytically found out. If you see this chip thickness ratio, there is a concept. Chip thickness ratio can be found out from the ratio of the T1 and T2. Okay. So, T1 is the undeformed thickness, this is the T1, I already told it to you. Okay. This is the T1, and T2 is the chip thickness, which can be found out from the chip itself. That means, here it is this line is perpendicular to this edge and this edge. So, then it will be T2 exactly, you can measure. So, this one is uncut thickness, this is the chip thickness. The ratio of the T1 and T2 is given as the chip thickness ratio. Okay. So, in practice it has been seen that this is roughly about 0.5, 0.6. Okay. So, that means, from here the conclusion is that after the deformation, after the plastic deformation takes place here along the OS, that is the shear plane. So, after this shear plane, the material which goes, it is already plastically deformed, and since it is, the ratio is 0.5, 0.6, that means the chip is expanded, okay, by 50 to 60% than the uncut thickness. That is what the conclusion is anyway. So, from here the T1 is equal to, from this triangle, if you see this, let us say in this triangle SN is the perpendicular to the rake face of the tool, all right, and SP, this is the extension of this line. Okay. So, this is, you are extending, this will be then equal to equivalent to the, or parallel to the VC. So, this is the cutting velocity vector VC direction. Okay. So, therefore, if this angle is alpha between the rake face and the line perpendicular to cutting velocity vector, then perpendicular to these lines, that means this line SN is perpendicular to rake face of the tool and SP is perpendicular to this line, all right, that means it is parallel to the VC. So, therefore, between SP and the SN, the angle will also be the rake angle. Between the SO and the direction of the cutting velocity vector is the shear plane angle. So, this angle if you see also will be the shear plane angle, because this line and this line are parallel lines. Okay. So, from these triangles, okay, from this triangle you can see that the T1 is equal to OS and the sine of this phi. From this triangle that is SN and the P, okay, you can find out that no, from SON, this triangle SO and the N, you can find out that OS is equal to cos of this angle, and this angle is phi total angle minus alpha, phi minus alpha. This is what it is shown here. So, therefore, the chip thickness ratio will be T1 divided by T2, which is sin phi by cos of phi minus alpha, OS getting cancelled. Then 1 by this chip thickness ratio, if we say, we are just inverting them, all right. By inverting them, afterwards we are opening that cos phi minus alpha like this. So, this will be then cos alpha divided by tan phi sin phi by cos phi plus sin alpha, because sin phi is getting cancelled here. So, the tan phi from here actually you can find out analytically that this is equal to the chip thickness ratio cos alpha divided by 1 minus T1 by T2 chip thickness ratio and the sin alpha. Okay. Now, here the phi actually can be then analytically determined, that this is tan inverse of, okay, phi is equal to tan inverse of this. Okay. I will say T1 by T2 cos of alpha divided by 1 minus T1 by T2 and the sin of alpha. See, alpha is known to us because it is the rake angle. This is the tool that we are using, all right. T1 by T2, if we take that value as 0.5, 0.6, okay, which is experimentally found out, in that case analytically we can find out the value of the phi. This is important because once we find out analytically the value of the shear plane angle, in that case many of the things without having the actual machining process or actual machine, we can actually find out those values analytically. This is the idea here, that how to estimate the shear plane angle, and through that how to estimate the stress, strain rate and so on. Let us give a few numerical examples. Numerical examples will be the direct implementation of whatever we have discussed now. Okay, let us see this. Let us say we have a problem that a mild steel workpiece is being machined at a cutting speed of 200 meter per minute with the tool specified as 0 degree, 8 degree, 5 degree and so on. So, it is in ASA. In ASA, I will remind you that if it is given in ASA, you have to understand that this is back rake angle, that is side rake angle, okay. This is the flank angle, principal flank angle. Here it is not principal, this is the flank angle, and these are the cutting edge angles, okay, gamma S and gamma E, all right. So, the depth of cut and the uncut thickness are 0.5 millimeter and 0.2 millimeter respectively. If the average value of coefficient of friction between the chip and the tool given as 0.5 and the shear stress of the work material is 400 Newton per millimeter square, then determine the shear plane angle and determine the cutting and the thrust components of the machining force. Okay. So, we have to find out the phi. Okay. To find out the phi, we have the formula, Marchant's formula, 2 phi plus lambda minus alpha is pi by 2. Here the lambda can be found out because this is given as 0.5, okay, the average value of coefficient of friction. So, since lambda, okay, lambda is what we have shown as beta there, okay, this is the equivalent, this is the friction angle, all right. friction angle, either lambda or what we have seen as beta. So, this will be the tan inverse of mu, okay, because tan lambda I showed it to you, right. Tan lambda is phi f by n and this is mu. So, therefore, lambda, which is the friction angle, this is the tan inverse of f by n or tan inverse of mu. Okay. Since mu is given, so we can find out what is the lambda friction angle, which here it in this case it 26.57 degree. Once we know that, then phi can be found out because alpha is given. Okay, alpha is given from here, if you see this. In this, we have to actually take the alpha value as 8 degree, because this is well, let us say why, this is also a question. 0 degree is the back rake angle and this is side rake angle. If you remember, I told you that the side rake angle influences the cutting force and the power, whereas what is the back rake angle? Back rake angle decides whether the movement of the chip will be appropriate, okay, not parallel to the workpiece and not entangling the workpiece. So, alpha s is the factor which actually works here. In this example, alpha s is the one that we have to take, because it is actually responsible for the power consumption and the force. So, we are taking this value 8, but not this 0. Here it is the alpha. This is we found out, that is the lambda, and therefore, we can find out the phi is equal to 90 minus this, okay, plus this lambda plus this, and divided by 2, because that is 2 phi and so on. So, this will be phi is equal to this. We found out the A, determine the shear plane angle. Now, determine the cutting and the thrust components. Cutting and the thrust components is Fc and the Ft. Okay, these are the two components that we have to find out. Fc, Fs first is Wt1 tau s by sin phi, that is the area and the stress, shear stress. W, you can find out W by geometry, that this is d by sin gamma p. Okay. This also I have shown it to you in the in our discussion when I was telling you about the geometrical parameters of the cutting process. All right. So, the d is given 0.5, this is 90 minus gamma s is given, this is side cutting edge angle, this is principal cutting edge angle. All right. Now, this will be equal to 2, around 2, that is 1.997, 0.5 by sin 90 minus 75.5. If S we found out, and therefore, Fs we have to then find out as W we found out as 2, T1 is 0.2, tau s given as 400 here, 400 Newton per millimeter square, all right, and sine of the phi is 35.715, 35.7715 we already found out. So, Fs will be this value. Therefore, the resultant force is Fs divided by cos of phi plus lambda minus alpha. Okay, this we have already derived. Then this will be Fs is given, phi is given, this we have determined, alpha is given. So, it will be R value we can find out. Okay. From this R value, we can find out the Fc value as well and the Ft value as well. All right. Fc actually is equal to 2 Wt1 tau s divided by tan phi. This can be derived from the Marchants actually. All right. And the Ft similarly from the Marchants we can derive this Wt1 tau s, sine of lambda minus alpha by sine square phi. Okay. So, I am not going back to the Marchants, and from you get the Marchants value and put it here, put it in the Fc. So, you can find out that this boils down to or simplifies to this expression. From here also you can find out that this is the Fc is equal to R into this. So, you put the value of the R you found out, or you can find out from here also. These are the two alternatives. All right. And similarly, Ft also you can find out, which is R sine of this, and these values are known now. So, you can find out. Alternatively, you can also find out by Fc is equal to Fs cos of lambda minus alpha divided by cos of this. Okay. This is a formula that we have seen in the Marchants. From here all the values are known, okay, and you can find out the value of the Fc, because Fs value we already found out, and here is the Fs value that you can put. All the angles we found out also, phi, lambda, alpha is given, that is it. So, Fc you can find out. Similarly, you can find out the Ft. Okay. So, you can see that this is a practical, this could be a practical problem, that you have the tool, you have these values. So, how to find out the shear plane angle analytically, or how to find out the cutting and the thrust component. See, another advantage of this is that you may not have the cutting process, but you can analytically find out the values of the Fc and the Ft, that is the point. Okay. Second problem, if you see, during orthogonal turning of a mild steel workpiece of 20 millimeter diameter with 150 rpm with a 0 degree rake tool, the forces normal to the shear plane and thrust are found to be this. Okay. If the chip thickness is twice the uncut thickness, estimate the power consumption in watt. Now, here also you can find out the Vc, because Vc is pi dn, all other things are given. Fc is, we also found out from the Marchants that Fn is equal to this. So, from here Fc can be found out as this equation, or there is a chip thickness ratio is T1 by T2, which is given as 0.5. Okay, here twice the uncut thickness, all right. So, therefore, tan alpha, this is for alpha is equal to 0 here, is will be from this formula r cos alpha divided by 1 minus r sin alpha, this will be r because alpha is 0. So, tan phi is coming out to be 0.5. So, phi is 26.56. Then we can find out the Fc value, because all other things now are given, Fn, Ft given. So, we find out the Fc, and the power is Fc into Vc, which is Fc you found out, Vc you calculated, and you multiply them, you can find out that this is 19.07 Newton meter per second, and Newton meter per second is equivalent to watt. So, this is 19.07 watt. You can see this is an alternative solution, because we have the formulas, these formulas as well. So, we can find out the Fc and the Ft in this way, and then we can have the Fc, all right, multiply by the V that you found out earlier, and you can find out what is the power. So, you can see that the problems can be solved in many ways, that is either in a direct way or in the in another way also. Okay. Here we will see another model. This is also a thin zone model, and the thin zone model, I already said that the thin zone we assume normally the deformation takes place in that area, it has certain area. Okay. So, it is not really a plane. So, that is a zone. So, the zone is a thin zone, and we are assuming that to be so thin that it becomes a plane, all right. So, here also this is a thin zone model, and this model is called the Lee and Schaeffer relationship. But why I wanted to discuss this with you, that this is another treatment given to the machining, metal cutting and the metal removal process, but the principle used here is different. If you remember, let me remind you that Marchant's principle is the minimum power consumption. Okay. During the machining process, the phi shear plane angle changes itself in such a way that power consumption remains minimum. This you will see in the Lee and Schaeffer, the principle is very different. Here the principle that they are using is a slip line field theory. Okay. Now, we are not going to discuss the slip line field theory in details, but we will be using the concepts only, all right. Let us see in this slide. This is the workpiece, here is the tool, and the chip is flowing along the rake face of the tool is shown here. Now, the cutting forces are transmitted through the triangular plastic zone ABC, where no deformation occurs. That they are saying that once again the cutting forces will be transmitted from here through a zone to this or vice versa, and it can be transmitted only when it will go through a plastic zone where inside no deformation occurs because of this force. Because if the force while transmitted from the shear plane to the rake face, if it further deforms the material, then it will not be transmitted one to one, I mean it will be lost. Okay. So, therefore, for the forces to be transmitted from here to here, it will go through this plastic deformation where no deformation occurs, it is already deformed. Okay. In that plastic zone, the entire material is plastically deformed, okay, maximally, and there will be no deformation because of the force going there, because force will always deform the material, right. But here we are saying that force is going through a plastic zone where the deformation is already has taken place. This is the assumption that they have made, Lee Schaeffer, because they considered that there must be a stress field within the chip to transmit the cutting forces from the shear plane to the tool face. Okay. I already explained it to you that what it is, that the force cannot be deteriorated, it cannot be reduced or lost. So, therefore, it has to go through a plastic zone where already deformation has taken place. Okay. In the ABC, the entire material is in the plastic state. This is stressed up to the yield point, okay, each point. Shear plane AB, this AB is the shear plane. Here the maximum shear stress occurs. Other slip lines, those slip lines are perpendicular to this line. Let us say this line, this line, this line, and so on, they are perpendicular to AB, and we have also drawn some parallel lines which are parallel to the AB, same kind of shear plane. BC is the surface, this surface, this is we are calling as a free surface, because no force is transmitted to the chip after it has crossed the line BC. See, what happens is that force is being transmitted from here to here, all right, and this is the plastically deformed body. So, therefore, forces will not be transmitted. Already once the force is transmitted, then the chip is formed and the chip is being removed along the rake face. Okay, the chip is formed here. So, slip line must meet the surface at 45 degree. This is the theory, and I said that the theory we are not deriving or describing, but according to the theory, the maximum stress where it occurs, that is the shear plane, makes an angle of 45 degree with the free surface. BC is the free surface once again, because no force is transmitted beyond this. Then what we do is that all of them, as you can see, these are very small letters. This is, we are designating the parallel lines as A, then here it is this line is designated as D, okay, and similarly this line is designated by something, it is not given here, and this line which is parallel to the AB is designated as C, and this line is parallel to the AB is given as let us say some value. Okay. So, we will find out that is A, B, C, D. Okay. So, this is once again, this is D, all right. This is we are saying as the E, this surface is E surface, this surface is D, and so on. This surface is A and this surface is D, sorry, this surface is C, okay, and there are parallel. So, altogether what I am saying is that there are parallel lines of the AB and there are perpendicular to that. So, all perpendicular lines are also the slip lines. Okay. Now, if we draw the Morse circle construction is a convenient means of relating these stresses on any plane on the principal stress. If you remember, we said that in the discussion during the stress and strain that cubic body can be unit cube body can be found out, which is already stressed, and there are 9 stresses, okay, 3 normal stresses and 6 shear stresses. So, for some reason this axis system can be selected in such a way that shear stresses are 0. Then all the principal stresses which are all the normal stresses which are acting can be called as a principal stresses. Okay. So, here Morse circle diagram, this is a convenient means to relate the stresses on any plane to the principal stress. Okay. Since plane BC, let us say this is the plane BC, let us say this BC we have designated as B, meaning that this is the plane and the stresses on the plane can be designated by a point which is B. Okay, we are saying this is B, point on the periphery of the Morse circle. All right. Now, this B is placed here. Since BC is the stress free, Morse circle must pass through the origin B, because this is designated as a B. So, Morse circle will pass through the origin, because this is the axis, here is the stress, here is the here is the stress, here is the shear stress, here is the normal stress, and here is the 0 point. Through this the Morse circle will pass. Point A, C, D and F are displaced from B by 90 degree. These points are nothing but designated as planes parallel and the vertical. Okay. These are the parallel planes, these are the vertical planes. So, A and D should be the parallel one of them, A and D, okay, parallel to each other, and C and F should be the horizontal. C is here, F is here. So, this is C and this is F, this is D, this is D and this is A. So, A, D and C and F, which will be at a 90 degree displaced from the point B, because the B and these lines you can see that they are at a 45 degree angle. So, when it is in the Morse circle, it will be twice the angle of the physical plane. Physical plane angle is a 45 degree, and in the Morse circle it will be 90 degree, twice this. So, this is displaced by 90 degree from the point B. Point B is the BC plane. Okay. Face E is this face. Okay, this face. E is inclined to the face D, this is the D, by an angle of phi minus alpha. Phi minus alpha, this angle we already found out earlier, because this angle is alpha and this angle is phi. Okay. So, you can find out that this angle is phi minus alpha. So, therefore, we are saying that face E, which is this, that is the rake face, inclined from the D, okay, D is perpendicular to AB, all right, and that angle is, let us say, phi minus alpha we are saying as the nu. Okay. Therefore, in the stress plane, the angle subtended by the arc AE, okay, this angle, this will be 2 and the nu here is shown here, this is that, all right. So, assuming uniform shear stress tau and the normal stress on the rake face, the friction angle can be given as tan inverse of tau divided by sigma. So, this is here we are saying that this is the Morse circle, here the vertical axis is the shear stress, horizontal axis is normal stress. So, therefore, this is the tau, okay, and SB is the normal stress. With respect to this E is the this is the rake face of the tool. From here to this, that would be the ES, this is the tau, and from here to here, this is the normal stress. So, tau, okay, sorry, the lambda is equal to tan inverse of tau divided by sigma. So, this is tan inverse of ES divided by SB, and this is the angle EBS. Okay. Now, this you understand that lambda, which is the friction angle, this is the tan inverse of F by N. Okay. So, F by N, F is equivalent to friction force. So, this is equivalent to tau, and the N normal force equivalent to normal stress. So, the lambda, which is the tan inverse of F by N, this we said as equal to tan inverse of tau divided by sigma. Okay. So, tau here is the ES and sigma is the SB. So, therefore, it can be expressed as tan inverse of ES by SB, and this means that this is the EB and the S angle, and EBS angle we are therefore saying as the lambda, okay, which is the friction angle. So, if this is the friction angle lambda, in that case the this angle EOS, EO let us say S, this will be twice that because it is at the center, all right. Since tan, well, this is explained actually, whatever I have explained here, this is explained here. Now, EOS, therefore, EOS is the 2 of this. Therefore, the EOS and the EOA or EOD, these two angles will give you the 90 degree angle, right. I am saying that EOS, this angle plus this angle EOD, this angle is a 90 degree angle, all right. Then this angle EOS, this angle is 2 of the lambda friction angle, and EOD, this is twice the nu, because nu here is this angle, and at the center it will be twice of that, all right, twice of that, because this is the nu. Okay. Nu means that is the angle at which this face is inclined with respect to the D, all right. So, therefore, you can find out that these two angles will be 2 lambda plus this is phi minus lambda, phi minus alpha, and this is equal to pi by 2. So, ultimately what we are getting is that the phi plus lambda minus alpha is equal to pi by 4. So, you can see that this is very similar to the Merchant's equation, but the principle at how they arrive to that is different. Okay. So, rest of the material we will discuss in our next session of discussion. Thank you for your attention.